and welcome to Astronomy. So we've been covering the geology section of our science, and we're going to transition into one of the other disciplines of astronomy. And sometimes astronomy is misinterpreted as just the study of outer space or stars. That's certainly part of it. But there's a lot to outer space and what we call the cosmos. And there's incredible things that link to just the geology you've been learning about in our science here on planet Earth that happen out there in the great cosmos. Looking at this right here, you might think, oh, this is just some kind of a graphic. No, it's a picture. It's an image taken from a telescope in outer space. And we're looking at the beginnings of a nebula, which is this beginning system of the birth of a star. So when you see this, is that what you really saw, the birth of a star, or did you just see a blob of gases and dust? Because that is what you're looking at, but more than that, you're seeing the beginnings of a new star. So our own sun started off much this way, where we would have material in outer space. So how do we get that material? How does that happen? And how do we get the birth of a brand new star for things like planets to begin to form around and begin to orbit? So in order to talk about our own solar system and sun, I think you need to have a background in our universe, or at least what we think as scientists caused the universe to form. So this can almost make your head hurt after you hear all of this, and you'll be like, I don't know about that. That's really a big stretch. Well, we got some scientific evidence that is pretty compelling. So I'd ask you just to bear with me. Regardless of what your belief systems are about how we came to be, let's just look at some basic science for a bit. And then not asking you to change your mind on any belief structure that you may have. What I am asking you to do is just learn some about this science that's here that we know about. Sometimes even the word Big Bang can get people to go, I don't want to hear any more. I'm asking you, let's hear some more. Let's learn about this term and what it really means, so you can have a better perspective, more well-rounded perspective about how we as scientists think the universe came to be. So we think about the cosmos in terms of everything that we see in the sky, but there's so much more than beyond what we can physically see. So the study of the universe is called cosmology. And I think that's an important term for you to know, because cosmology is kind of an encompassing term, and there are a lot of different, what I would call disciplines of astronomy, and different experts in the field, from physicists to chemists to geologists, that all have an emphasis in the astro world. So I had a student who wanted to start off as a geology major, and then they got into a master's program, and they found their world into physics, and the world just took a turn for them. In fact, outer space took a turn for them, and they began to work with NASA and began to map lava flows on Mars, and then began to do some really cool things with other outer space, and I might add on planet Earth. My point is this: there are jobs out there related to the study of the universe. And this is something that a lot of people are curious just by nature about. So let's talk about, how old do we think the universe really is? Get past that. What is the Big Bang? What is cosmic inflation? Some terms. You're going to learn a bunch of terms today and how they kind of fit together. My goal is to get from the really big picture of how do we start the universe down to the different types of galaxies, and then go even more to the micro level of suns. What are the different types of stars? And then apply that to what we have and that we're a part of. What is the system of stars that we in our solar system are a part of? Our next lesson will focus on our solar system, and then we'll kind of broaden back out and look at some of the really important astronomical events that occur. So this is a really interesting unit. Let's start with the age of the universe. You might wonder, how can we figure this out? A lot of it's done on mathematical models, so let me kind of just put that out there. Also based on dating of stuff that we get from outer space, and then understanding based on how our telescopes operate today, the depths of space, the furthest places away from us, how old that light must be traveling at the speed of light. When I said your brain may hurt, if you really start thinking about what we're seeing in terms of talking about astronomy, the light we're seeing from things that might be 100 light years away, or let's say 1,000,000 light years away, you begin to see, okay, the speed of light, okay, you get that, you start putting that math together, the kind of distance we're talking about. Space is huge. So we think our universe is right around the 13.8 billion, as in Bravo, years old. Wow, 13.8 billion years old. So how do we understand that? How do we even relate to that? Where are we in the Milky Way in relationship to all of these structures that are 13.8 billion years old? So scientists had some really tough questions to answer, like, is the universe going to stop expanding? Is it going to collapse in on itself? These are still questions that are up for debate, quite frankly. And to our surprise, it is still expanding. That's an important piece of information. But what we know is right around 13.8 billion years ago, the universe expanded pretty darn fast, and it was faster than the speed of light. And so when this happened, things kind of got a little out there in outer space. We call that the cosmic inflation. When this stopped, the energy driving this force of expansion transferred into matter. Matter being like things you can touch that you and I can relate to. If you're sitting at your desk, that's matter, right? And then matter and light. And this created what scientists refer to as the Big Bang. So I think sometimes people just think this kaboom thing just happened and everything started. I can't be the one that answers that's exactly how things went. But we know there was an event that created enough force for matter and light to have something remarkable happen. So after we get this big event that happens, a few minutes later, just a few, we're going to start to see something remarkable. This remarkable event is responsible for the first elements of the universe. And this is because protons and neutrons started to, and as they start to collide, we begin to get our first elements such as hydrogen, helium, traces of lithium, beryllium, the beginnings of our universe elements as we know it. We call this important stage nucleosynthesis. And literally just a few minutes after this important marker of getting our first elements, the universe had formed a majority of its helium. That's going to be important to our own solar system as we learn about some of our planets that are beyond Mars in our own backyard. It's a big backyard though. And then we know that after this event occurred, the nucleosynthesis stage, we would have a universe that had expanded in size and began to start its cooling process. This cooling process is super important because we have some evidence that this rapid expansion occurred and that temperatures of the initial Big Bang, we actually have some, if you want to call it residue, left behind. So let's examine that. So this residue I'm talking about is actually radiation from the Big Bang. So it's the original stuff that happened at the beginning of the formation of the universe. What makes it a challenge is humans can't physically see it. with our eyeballs, but we can see it with technology that we have. In fact, it can be clearly seen with microwave part of the electromagnetic spectrum. That's incredible because this is an image of what we can see in the cosmos in your diagram here, this graphic. And what's important to know about cosmic microwave background radiation is it's not uniform all over the universe, meaning it's not exactly at the same precise temperature. It rests right around, this is an important number, 2.725 degrees above absolute zero. So absolute zero theoretically is when everything stops operating. Matter stops moving is what I mean. But this sits right above it, but it's just like this afterglow, if you want to call it that, of the Big Bang that exists throughout everywhere we can find in outer space. So it's all over the space, all over the page. Until this was discovered, Big Bang was kind of what I would say a theory that was highly controversial in the scientific community. Cosmic microwave background radiation was kind of that smoking gun that gave scientists a place to agree on that, yep, we had an event that started the solar system as we know it. So the next phase of our universe's background, its history, happened about 200 million years after this event. So it took time, deep time, in fact, for things to kind of coalesce and things get moving. And we had a period called the Dark Ages. So the universe became dark after the Big Bang, and we got our first elements and so forth. But we had a variety of key elements out there, such as hydrogen atoms, helium, trace elements, heavier elements. And it's going to take time for them to do something with all of this, meaning for the way that physics works, the way that chemistry works, to all come together to make what we know as the universe today. So we went through that period of time where we have the Dark Ages and all that stuff's out there. And something happens to that stuff over time. It's going to begin to come together. It's going to begin to make lumps and clumps and start to make mass. And as it does, those masses of dust and gas and the elements start to work together to make a denser clouds that become more massive, and they start to attract more of the other matter that's out there and becomes more compact. And then we would get our centers that would start to have the nuclear fission, and boom, we have our first stars are born. So the first stars come to be early on in the existence of the universe's history. And over the next 100 or so million years, we would start to get our oldest stars of the universe. So if you start to think about where Big Bang, where everything started, that's really the center of the universe, and everything's been expanding outward. So the stuff that's farthest away from us, theoretically, is the oldest stuff in the universe. So we came a lot later on in terms of the Milky Way. So over the course of 1 billion years or so, ultraviolet light from these stars broke down, it ionized the hydrogen atoms into gas. And when it did, it would allow stars and galaxies to transform the gas that was in them to be transparent light like we see today throughout the universe. So this reionization stage was an important thing because that basically translates into what we know of stars in the universe and how they give off light today. Going back to the light thing, the speed of light is extremely fast. And if we're seeing light that's coming from Big Bang, or theoretically the stars that came out of the first few stages, like our first star stage into the reionization phase, we're looking at things that are potentially 13 or 12 billion years in age. They may not actually be in outer space anymore. They may be gone, but yet the remnants of the light still travels that far. So that's kind of the mind-blowing aspect of thinking about why this is such a deep topic, deep space, is it begins to realize that there was a long process that went to making all this happen. There's another really important term for astronomers and you as an earth scientist, that it represents the explosions of stars. So once a star is born, when they come to their end life cycle, they explode. And what happens for this explosion is you end up burning up pretty much the fuel that's inside of the sun, a sun, not necessarily ours. Ours will go through this stage, but what will happen is the nuclear energy in their cores keep burning and create this extreme heat that keeps it from collapsing. At some point, that star runs out of gas. It starts to cool down, not allowing for that nuclear fission to really take place. And this is when the star collapses in on itself. When it does, kaboom, it's going to go out in all directions, and it's going to create this massive, massive explosion. One of the most incredible things in outer space that creates the birth material of new stars. Give me a drum roll, please. We call these supernovas. When a star explodes, the elements in them explode out into outer space. This is the stuff that can create new young baby stars. Supernova can occur several different ways. You can get two stars that collide together, kind of like you see in this illustration here. And one of them tends to be a white dwarf sun, which I'll talk about in just a few minutes, which is about the size of the Earth. So a white dwarf is what remains after a star like our main sequence star today, what we have in our solar system, runs out of gas, runs out of fuel, and it collapses in on itself. So if the white dwarf collides with another star, it pulls a lot of their material away from it, the matter that is, and then it can create a supernova. 2 or 3 of them occur in the galaxy like the Milky Way every century or every 100 years. That doesn't sound like very often, does it? However, our universe has just an uncountable amount of galaxies out there, and scientists now have capabilities with these so advanced telescopes to look into outer space and see like 100 of these every year. So we can document them and see what's happening. We can rarely see them on planet Earth because we have dust in space that's blocking our view to get a front row seat. But you get into where we are putting these remarkable telescopes, you can get a pretty good front row seat. So if you were, in outer space, let's say in a spacecraft, you might be able to see one of these if you had the right equipment to do it. But we can take photos of them from our telescopes, and that's pretty incredible. So you're looking at one right there, and look at the brightness of that, and you're like, wow, pretty cool, right? So again, supernova, the birthplace of brand new stuff that can make new stars. It's the death of one leading to the potential birth of another. By studying these events, we have discovered that supernovas have the right chemical makeup that create our brand new stars. And that is pretty much how new stuff is made in the cosmos. So we know that in outer space, elements like hydrogen and heavier elements like carbon and nitrogen are needed to build the building blocks of life. Now, I'm not suggesting to you that every galaxy has advanced life forms or any life forms. I'm telling you it's possible because the building blocks of life as we know it on Earth do exist in outer space. So the next important topic is what dark energy and dark matter are. As scientists, we have to own when we really don't know all the answers. And any astronomer would tell you, any astrophysicist, I think, would tell you, we know a lot, but we certainly have a long way to go. Just like every oceanographer would say, we don't know everything about the ocean and everything at the depths of the ocean, but we're learning. And I think that's the case as we start to look especially at dark matter. The percentages of each matter, no pun intended there, but dark energy comprises about 68% of our universe, of all the stuff that's out there. Then we have 27% made up of dark matter, which we'll get to in just a second. Everything else, the remaining 5%, is other normal matter as you and I know it. So to us, 100% of what's on Earth makes up part of that 5%. But in the universe, in its realm, that's not so much so. So what is dark matter? Dark matter is not the same stuff that makes up stars or planets. It's something else. It's not dark clouds or normal matter like baryon particles. And it's not a giant galaxy-sized black hole. That's often a misnomer of what dark matter, dark energy is. Matter can be described as baryonic in nature. So the stuff that makes it up is tied up in dense chunks of heavy elements. We call those elements macho elements. Gotta love them, right? They stand for massive astrophysical compact halo objects. Wow, what a mouthful, right? Machos, I like that better. So dark matter is made of stuff, but not the same stuff that you and I can touch. Another more accepted theory is that dark matter is made up of more exotic particles like axions of WIMPs. Another cool term, right? WIMPs stand for weakly interacting massive particles. So the stuff that you're seeing in this picture, a lot of that stuff is dark matter. There's dark energy out there that we can't really see. Some really amazing stuff. So whether it's machos or WIMP that makes up dark matter, it's stuff that's not the same matter that we have on planet Earth. So matter in the universe comes in just about every form you can think of. Solids, liquid, gases, even plasma, which will be important when we're talking about stars in a bit. And matter, as you and I know it, comes with a subatomic particle. It has a mass, right? It has a mass of its volume. So it's like how many protons, how many neutrons, how many electrons, even neutrinos. These are what dictate on the periodic table what we know of as elements. And when we think of matter, we also need to think that there's a component that's just the opposite. It's its twin, but of the opposite type, called antimatter. And for understanding that, just think of it as its other side, its twin, but it's of the anti-version of it. Scientists think that there was an extra matter particle that was made when Big Bang occurred for just about every antimatter pair. So basically for every element, for every billion antimatter particles that were made during Big Bang, we get another particle of antimatter. And that's why it exists in the universe. So for every proton, you have an antiproton. For every hydrogen molecule, you're going to have an antihydrogen molecule. So the matter has an anti-component for it. Let's move into another really interesting aspect of outer space, and that is black holes. Most people have heard of black holes, and we can actually, as scientists, document that they occur in terms of seeing something remarkable with telescopes in outer space. So a black hole is huge concentrations of matter that's densely packed into one very small opening space. What happens is that we know right around where the black hole's surface, its outer part of it exists. We call that the event horizon, and that gravitation that pull is so incredibly strong that nothing can escape it once it's in the hole, and light can't get out. Now, I'm not even going to begin to talk about what happens in the hole, because I'm not sure I really can answer that question, and that all scientists know what happens in the hole. We have theories about it, but realistically, until we can test that hypothesis, I'm not sure I'm willing to go down that road yet. That would be a great physics class to take to learn that answer. The event horizon, though, is an important place in the black hole because that's where all the matter is that makes up a black hole. So you're wondering, how can we see these in outer space? We can see matter being consumed into a centralized location. So here is a NASA view of kind of how a black hole works around the event horizon. And you can see all this stuff just being pushed into one singular area, and that would be the black hole itself. So I wanted to show you this because it's a kind of hard to visualize what it is, since light's not being emitted back out from outer space from one of these things. We have to rely on a different technique to see them. So now that you've learned about black holes, let's move on into another topic, galaxies. So there's a variety of galaxy types, and we're going to cover the majors. So spirals are some of the most common. These galaxies have giant, literally pinwheel-looking structures that are constantly packed out with star material and stellar gas and nebulas and all that great stuff that makes up galaxies, even potentially black holes. We know that galaxies have them. So all spiral galaxies have something in common. They have a bulge, which is a tight concentration of stars and material at their center. And then they have these arms that look like pinwheels that are tightly wound or loosely wound around the middle. So not all spiral galaxies, again, are one size fits all. Depending on how their arms are wrapped, they have different names for the types of galaxies. Most spiral galaxies are surrounded by halos, which are mixtures of old stars that have died out or exploded. And then they have star clusters and dark matter that exist in them. So spiral galaxies, that's an important type of galaxy that we'll look at even for our own galaxy. Let's look at elliptical galaxies. This type of galaxy ranges from just being a simple circle to more of an oval type of shape. And they are much more rare than spiral galaxies in the universe. They contain minimal gas or dust and don't have an organized structure like spiral galaxies do. Stars orbiting the core are kind of traveling in random directions. So this could be a place where you could have some collisions happening. And literally, we find that the stars in these galaxies are older than what we see in spiral galaxies for the most part. So the theory of how these galaxies form are typically by the collision and merging of other older spiral galaxies. So the next type of galaxy is called a lenticular galaxy. Consider them the hybrids of spirals and ellipticals. That's exactly what they are. They're kind of missing the arms of the spirals, but they have kind of the randomness of ellipticals, and they have older stars in them. They typically have very little new star birthing occurring or formation. The theories on how they form are there are basically two theories. Older spirals that have faded out arms and mergers of spiral galaxies to create what we call lenticular galaxies. Irregular galaxies are those that just take their name. They're odd in shape. They can be from anything from toothpicks to kind of little groupings of stars to ring shapes. They can just have kind of an oddball shape altogether. But they contain a lot of dust and gas, so there are places where new stars could be born for sure. Irregular galaxies' shape are thought by scientists to be the result of interactions with other galaxies, the gravitational pull that makes their kind of irregular shape. So this galaxy can definitely contain old stars, but because it has so much of the interstellar stuff that we need to make new stars, this is where you're going to see that happen. All right, what is an active galaxy? This type of galaxy can be any type that we've learned about thus far, but the active refers to its center. Okay, so there are two types, radio loud and radio quiet. So what's the difference on the two types of active galaxies? Radio loud means they emit light from both the middle, the disk itself, and from its jets. And you can see that in this picture right here. Believe it or not, this is a real thing from outer space. Radio quiet has the light emitting from its disk, but not from the jets on the side. So it's just kind of a big light. So active galaxies literally have their centers hundreds of times brighter than the combination light of their stars. So that's kind of an interesting phenomenon. And about 10% of all galaxies are active, and the Milky Way is not one of them. So, out of all of those billions of galaxies that we have, only 10% appear to be active. It'd be really cool to see this in outer space. So, scientists think that this excess energy that creates an active galaxy is derived from areas existing near black holes. The next type of galaxy is called a Seyfert galaxy. This is the most common type of active galaxy that's out there. Looks like a normal one if you saw it with visible light, but you need a different type of system to interpret it. You need infrared radiation to see it because they emit such a strong brightness, and they have like a donut shape where they're round with a middle section in the where that big active light structure is. They also have lower radioluminosities than other galaxies. So there's two types that exist. Very easy, type 1s and type 2s. Type 1s exhibit unusual features and their visible light with rapid motions near their cores. And then the type 2 exhibits features that move on a more slow basis. Quasar galaxies is another type. These are the most bright or luminous of active galaxies. They emit light across all of the electromagnetic spectrum, making them very special, and they can create these really strong propelled particles of jets that radiate an incredible amount of energy from their centers compared to what we have in the Milky Way. There are about 1 million quasars that have been identified thus far, and we have some that are literally 13 billion light years away. I need you to think about that. 13 billion years, and then the universe, how old did we say? It was a little older than 13 billion. That means that this is some of our oldest stuff out there galaxy-wise, so that's pretty incredible. While blazar galaxies seem very similar to quasars, are a little different. They have their light pointing towards Earth, which appears to make them brighter than other types of galaxies that are active. But scientists can detect them using energy particles like neutrinos, and we can trace their jets back to where they originally traveled from, their original space location. And that is incredible because what we have found is it gives us insight into how black holes operate, because most of these galaxies that are active are near some type of a black hole. And so this type of galaxy, we can actually kind of map it back to its original location, birthplace. Our neighbors are the large and small Magellanic Clouds, and these guys are only about 160,000 light years away, so they're pretty close to us in terms of galaxies to the Milky Way, but they aren't visible from the northern hemisphere. So you got to go down to the southern hemisphere if you want to take a peek through a telescope. Andromeda Galaxy is bigger, and sometimes you can see that from the northern hemisphere, and that is about 2.5 million light years away. But there are other galaxies beyond our neighbors that we can't see without the help of technology, specifically certain types of telescopes. But galaxies exist all over the universe, and so there are billions of them, and that's almost incomprehensible when you start to think about just the distance between Earth and our moon, and you start to think about the immensity of outer space. That brings us to our Milky Way galaxy, and we are a spiral galaxy, so we are the most common type of galaxy out there. It gets its name because on a clear, dark area, this area is actually in New Mexico near the VLA. This is the VLA, very large array. I've been there, and I can tell you the Milky Way is visible on a good non-cloudy night. And you can see because it looks like a band of milk out there in a grayish thing. And I can't tell you how awesome it is. If you've never seen the Milky Way, get out of town, go to a dark place on a clear night and look up at the sky. Back before we had light pollution, the Milky Way was a very visible thing. And I just can't tell you how excited it is I get every time I see it. To this day, it never gets old. So all the stars we see at night with our visible naked eye are in our own home galaxy known as the Milky Way. Which brings me to talking about stars, which is the makeups of galaxies, or at least one major component. So all galaxies have them. So let's talk about what stars are. Like our stars develop from clumps of gas and dust, planetary nebula stuff, these that form these stellar nursery stuff, all that stuff that we need to make brand new stars, and that takes hundreds of thousands of years, sometimes longer. And as these clumps gain their size and matter, they start to spin. And as they do, they begin to heat up just naturally because of friction. And once we get a core and that core heats up to millions of degrees, a remarkable thing happens. Nuclear fission, that's what we talked about for these, right? We were talking back on how stuff forms with the Big Bang and the original stars. So a star gets born when that nuclear fission occurs. So from beginning of the birth to its death, let's talk about the different types of stars. Stars start off typically as the main sequence star, which is where you get that nuclear fission occurring in its core. Main sequence stars make up 90% of what's out there in outer space for star-wise, and so they're super common. There's no standard rubber stamp of, oh, they're this size, they're about this big, they're this color, they're this bright. They range from much bigger than what we have our sun, 200 times bigger, to just a fraction of the size, a tenth of the size. Size matters because that means that's where the core of the energy is. The energy that it creates can dictate how long it can survive. So some only last for millions and most last for billions of years. What happens to a main sequence star after it runs out of gas, basically, or as it starts to run out of gas? It turns into a red giant star. That's the next phase. So this happens and the star begins to collapse in on itself because the energy that it takes to burn in the core by fusion, it's constantly fighting that expansion and gravity pulling stuff inwards towards that. When this process, you hit an imbalance because you're not burning as hot, that's going to squeeze all that temperature into towards the center. And the stuff on the outside can't be retained. So it starts to expand. And as it expands, you start to get the outer layers of a sun's atmosphere that begins to go much bigger than it used to in size. So the outer layers blow away, and that causes the sun to expand in its appearance. So let's just say this happened in our solar system. Even planet Earth would be consumed, likely even all the way to Mars, but we would have the inner planets as part of that red giant star umbrella. We would now call that a planetary nebula. What happens past the red giant stage? We move into what's called the white dwarf star stage. This is when the red giant loses its outer stuff and it's finally blown away, and all you get behind is the core. So the core is literally about the size of Earth, but the density is much, much more dense than anything that would be the same size comparatively. So important to note that white dwarfs aren't creating fusion anymore. So there's no heat coming out of them, and eventually they cool over billions of years. That brings us to the neutron stars. These are the stars that are stellar remnants. They're not even in the white dwarf stage anymore, but they pack in a huge amount of mass. And just as a comparison, a neutron star could have as much mass packed into an area that we would consider Long Island in New York, both in length and width, but everything that you can imagine our sun having mass-wise into that small little size. That's almost incomprehensible. But after these stars go through these sequences, these stages, and new stuff starts the process all over again. So why should you care about all of this? We just covered a whole bunch of stuff, didn't we? And we hadn't even gotten to our own solar system and our own sun. What are you looking at here? Well, this is evidence of when the non-avian dinosaurs went extinct at the end of the Cretaceous period. So what's the big deal about this 65, 60 million year old layer right in here? Well, that was caused by a very important collision with planet Earth from something in outer space, an asteroid, meteorite, big one, 6 mile wide, got smashed. So why do we care about all this? Because outer space not only tells us how the universe was made, its age, it also tells us what's happening to our own neighborhood Also, we can learn from stuff like the asteroid that smashed into planet Earth that is contributing to the extinction of non-avian dinosaurs. And we look for these things. We study outer space to try to preserve Earth as we know it so we don't have an extinction level event like they did with the organisms that lived back in the Cretaceous period. So astronomy matters. Astronomy matters to our survival on planet Earth. If we were to colonize another planet, it would matter even more. So these factors are all part of the equation of why you should care. When we come back in our next lecture, we'll be learning about our own solar system. And then the last part of our astronomy will be looking at how do we study outer space and some of the cosmic events that occur that are a big deal. So thank you for your time today of absorbing things like the Big Bang, the different phases of the universe that it's gone through, and then how do we make stars and galaxies, and then the different types of stars, because they're a big deal. And you need to know what type of star that we are. We're that main sequence star. About how old we're going to be, you'll learn that in the next lesson, how old our star is. But I think you can get the gist that our star is probably billions of years old. The question is, how much fuel does it have? Stay tuned because you'll learn that in the next lecture. See you at the next stop. Bye.